Hello, my name is Vin Sharma. I'm responsible for the Amazon SageMaker Neo service team at AWS. AWS has a number of machine learning services, and SageMaker Neo is one of them. It's part of the SageMaker portfolio, and I'm here to talk with you about how we use that to enable machine learning models to run on edge devices based on the ARM Cortex-A architecture. And we're really excited about a number of devices that have been enabled in this fashion through the cloud service. So you can train your models in the cloud and deploy them on edge devices at scale. So without further ado, let me dive into how we do this and what you can get from this experience. Much like hundreds of thousands of other SageMaker customers who deploy models in the AWS cloud today, we wanted to provide a capability to other customers that want to deploy those models also on edge devices. And we see that there's a number of use cases where customers bring to us models that have been either already trained in TensorFlow or PyTorch or MXNet frameworks, or they come to the SageMaker platform in AWS to build those models from scratch. And we see that today almost 80% of or more of deep learning workloads run on AWS, and over 85% of the TensorFlow workloads, TensorFlow models are built and trained on AWS. It's for those types of use cases where customers build and train models from scratch that we see an end-to-end workflow that enables them to do that easily. So much more important than providing individual tools by themselves. You could certainly build these models offline on your own infrastructure or on AWS using the standard capabilities of the cloud platform. SageMaker makes it that much easier to build those models by helping you bring data into the development environment for machine learning, prepare and transform that data for training purposes, provides you with a number of pre-built, pre-configured notebooks that make that task simple. At the same time, we provide a number of distributed algorithms that have been parallelized for high performance and tested to work with the AWS cloud infrastructure for both compute and storage. We, in SageMaker, provide capabilities to deploy those training jobs at scale from either a single machine instance to up to 256 instances in some cases, if you get the scale for that cluster and you need that scale. We also have a number of capabilities that let you train and tune those models. But the part that I wanted to focus on in our session here today is the task that sits between the time that the model has been trained for the best accuracy that you can get from it, and the stage of deploying that model in production at scale, whether it's in the cloud or on edge devices. And in our case, the concern is specifically edge devices based on the ARM AR64 architecture. But it's the optimization task that we find presents a significant barrier to customers and machine learning developers that want to deploy these models and get the best available throughput or latency from that model on a given hardware. And the reason for that is that there's a number of complicated subsystems involved in delivering the best available performance, whether it's latency or throughput, for a given model on a given hardware. You certainly have the process of building the model with either your own algorithms or those provided by AWS. But once you've trained the model, when the time comes to deploy it either to the cloud or to the edge or both, there's a lot of depth to the analysis of the model. Certainly the model has been trained to deliver the highest accuracy, And with that come a set of assumptions about what how you do that, including using certain layers or functions that are available in the framework for that particular task that the model is designed to do, which in turn creates significant overhead when the model runs on a particular edge device. So let's look specifically at simply the fact that the accuracy is often a trade-off with the performance or even the size of the model. As a model okay. Let's look at what makes it difficult to optimize models for inference on edge devices or even in the cloud. Fundamentally, there are a number of reasons why models that have been trained for the highest possible accuracy tend to cause constraints, cause problems for developers that want to then deploy them in production. Let's unpack a few of these in detail. The first of this is just simply that when you build a model and you train it for accuracy, there's often trade-offs related to the size of the model as well as its performance. Typically, models that are more accurate require a lot more. If they're deep learning models, tend to have many more layers that perform a number of processes to transform the input data into the expected output. With that comes the additional computational cost of performing those functions. And that often has a very clear effect on the performance as measured by the latency or the throughput of the model, how it handles the input. What that means fundamentally is that models aren't trained from scratch to be compatible with a specific device, particularly if it's a resource constraint. If it's resource constrained in terms of the number of flops available for compute, or the more often than that, the more expensive memory that's available as a footprint for the model. So that's certainly an area where we think that providing an execution environment that consumes the smallest available footprint on the device hardware would be a benefit to customers that want to deploy models on edge devices. The next problem is similar in that even when you have done as much as you can to reduce the size of the model itself, perhaps through compression techniques, there's still the challenge of being able to find the execution environment that's compatible with the edge device and optimizing that execution environment. And if in this case you built your model in MXNet or TensorFlow or PyTorch, the expectation is that you would run the model also in PyTorch or TensorFlow or MXNet. And then the challenge is to be able to optimize PyTorch for Cortex-A based device or TensorFlow for Cortex-A based device, which often leads you to the path of taking a more mobile or device optimized framework, such as, say, TensorFlow Lite as the alternative. We believe that there ought to be a way in which you could create an execution environment that's compatible with models built in any framework. So regardless of whether you've built the model in MXNet, PyTorch, or TensorFlow, or saved it from some other format into some other framework into Onyx, you still need to be able to run that model on a device without having to swap out the framework or have multiple frameworks running on the same device, which can be extremely resource exhaustive. The third issue is that the optimization of the framework or the model for any particular device or any particular hardware from any given framework within an organization that uses many of these. There may be teams within an organization that prefer MXNet, and others that prefer TensorFlow, and others that prefer PyTorch. They may be deploying these models on a variety of device architectures, or for any given architecture, such as, say, ARM v8, you may still need to have devices with various different designs from different vendors, system on a chip providers. And so for all of this variability, there's multiple pathways to go from a given model, from a given framework to a particular architecture. And this causes a significant pain for developers who are either unaccustomed to the particulars of a particular hardware, the specific hardware, or to a framework. So for example, the most common way of handling this is to use some kind of a compiler or converter that's available in the framework, but that means then that you're tied to the specific framework for your development, and you depend on the compiler or the converter provided by that framework, and all of the hardware that it is designed to optimize to. The other option is to use the hardware to standardize on a particular hardware. And in this case, if you've picked ARM as the platform and the compute library that's provided by it, that's certainly a really good option for a variety of models and frameworks that are integrated with it. And yet you may miss out on some available performance for certain specific models, or the breadth or addressability or the portability of the model. So this was the heart of the reason for our service. We decided to build a capability that lets you train in any one of the frameworks with any available algorithms from SageMaker, but to be able to then deploy those models and run them on any target architecture. This is a fairly broad agenda and a large charter. That said, we focused primarily on the most popular device architectures and cloud systems that are available on AWS. And as we go forward, we continue to add additional platform hardware as well as additional frameworks and model types. But the heart of this is a service that we call SageMaker Neo that allows our customers to bring a model that's trained either in SageMaker or anywhere else, but to be able to optimize that automatically for any chosen target hardware. And in this case, if they were to deploy to edge devices based on ARM, then they would select the ARM-based edge device either as a device type, as a particular device, or as a architecture specification with the operating system, the system library as the target. And we would compile as a service that model at no additional cost and be able to deploy that on the device of choice by using our runtime. So this is the heart of our service. We believe it makes it really easy for customers to now deploy models on a variety of target hardware but specifically get the best available performance for that model on that hardware. If, for example, some of our most recent successes have been both internal to Amazon as well as external, we've had a number of successes with computer vision models, specifically image classification and object detection models, such as MobileNet V2 for classification, or SSD, single shot detector for object detection, or YOLO. This is in addition to audio models where we've had keyword detection, so a device that would need to wake up when you speak its name is a really good example for where the Neo service has been able to add value by improving the performance of the wake word or the keyword detection model, but also reduce its resource consumption so that it consumes as little of a footprint in memory and compute, leaving room for other applications that are more critical, like playing music. The way it does this is, as the slide shows you, fundamentally like any compiler would. A compiler typically starts out with being able to parse a source program, do a series of transformations, and during those transformations, optimize the execution, optimize the program for execution, and then generate code given the target hardware on which that program ought to run. And so fundamentally, Neo is a compilation process delivered as a cloud service where it parses, in this case, the program being a specific model trained in the particular framework, and it converts that framework-specific format of the model into a representation that's common and independent of the framework. This allows the compiler then to perform a series of common standard optimization techniques or methods and passes over the graph or the computational graph of the model by detecting patterns in the way that the inputs are being transformed or the layers are conjoined, so we can then fuse those layers and reduce the complexity of the computation. We also do a number of hardware-specific optimizations in the next stage that tie this to chunking the model for specific hardware based on its instruction set architecture and its and memory hierarchy. And then ultimately we generate a representation of the model that can be consumed by a low-level compiler or low-level code generation mechanism, and that generates the machine code ultimately. So it takes the model in its original framework-specific form and converts it into a hardware-specific form towards the end of this process, and then we provide you the ability to run that at scale. So if you dive in a bit more into the details of how this works, if you imagine a model trained in PyTorch, saved as a PTH file, we then have our customers come to the Neo service either through the console, the AWS console, or an API or the command line, and submit this model from their S3 bucket, the account in which they have an AWS account, and the S3 bucket then provides us with a standard location from which to read the file. We then, the service then on behalf of the customers or the client's identity, using their credentials that are provided to the service for just this particular task, securely obtains that model within the service, converts it, compiles it, and returns the converted file back to the S3 location to our customer. No human, no service team member certainly has access to the model. The service itself is operating in the customer's account and has access only to the customer's files. And so this is an entirely automated process. What that means during the process is that we do a number of graph level and tensor level optimizations for those interested in the details. These are fairly well-defined compiler techniques that have been in the industry for a while, but what's novel is and interesting and certainly technically challenging is being able to apply them specifically to the types of programs that deep learning models and more broadly machine learning models represent. And what that means then is that we take the graph, and some of the hardest problems that we've tackled in the past year have involved being able to annotate the computational graph of the model by tagging specific nodes for the type of hardware, the accelerator on which they ought to be placed, and then stitching the results back in such a way that the end customer's experience is that of a highly performant model, but the complexity of partitioning the graph across the CPU or the GPU is hidden and simplified. So a large part of that involves us being able to do some significant model analysis, but also hardware-aware optimizations such as tiling and tensorization. One of the most interesting things about the compiler here is that the entire project from the Neo service team is a part of an open source effort. We are active contributors and committers to Apache TVM, which is the open source project around which is one of the compiler technologies around which the Neo service is built. And so we do a lot of this work upstream in the open source project. We have published papers that reflect, that represent and describe the work that we've done in these optimization techniques, including being able to compile quantized models as well as do this graph level optimization based on partitioning and handle model dynamism, which has been one of the hardest problems to do, is to be able to handle a diversity or variability in the input shapes or in the way that the data-dependent computations execute in order to provide the best available performance for a given model with variable inputs. So all of this work happens as part of an open source project to which we contribute. We also integrate with partner-provided machine code generation tools and compilation backends. And so the Neo service essentially then is a synthesis of the various open source, partner-provided, and AWS-developed technologies that together deliver the best available performance for a given model from any of these frameworks for the given hardware. And this is where we continue to innovate. In order to take advantage of the model after it is compiled and to run it on a variety of devices, you obviously need a runtime that's designed for each of these device hardwares. And so we build and provide that as an open source library that you can integrate into your application. And with that, there is a clean separation of the model from the application. It allows you to update the model independent of the application, to load the model into this runtime. As the model updates independently, you can reload the model, unload the previous version. And it also means then that this runtime takes on the task of dispatching the model and parts of the model to the right backend, whether it's the CPU or the GPU on the SoC, and we deliver then a performance that scales with the compute resources of the hardware. Both the compiler and the runtime, as I mentioned, are open source. We have an active development and deployment mechanism to bring those from the open source projects where they tend to evolve very rapidly, but to test and verify and perform a series of certifications across the device hardware architectures and the cloud service platforms to make sure that what we deliver in the SageMaker Neo service is a stable and scalable and secure version of these various compilation technologies, including TVM, as well as Treelight and the partner-provided components that together constitute the compilation service for a variety of hardware. And if you're a device vendor or a hardware provider, a processor vendor that would like to integrate with this cloud service, then we make it really easy to do that through the open source project, but also through the testing and regression that analysis that we do for models, over 2,000 of which we run on a nightly basis to verify that the performance is at scale and consistent. So with that, when you put this together back in the context of how SageMaker provides a complete end-to-end workflow, it means then that not only do we have tools and notebooks that make it easy to build, train, and scale the training of the models, but we also have a mechanism that automatically optimizes the model for deployment, and then tools subsequent to that in that chain to deploy the models either in the cloud or on edge devices, such as using Greengrass or any other cloud service that allows you to pull the model from the S3 location where it was stored after it was compiled and deploy them at scale to the edge devices and manage them at scale on those on that fleet of devices. So with that, I want to sum up and close by summarizing the capabilities of SageMaker Neo as it's used now for a variety of ARM-based devices at scale, as providing this portability of the model from a variety of frameworks to the device types, and certainly accelerated inference using software-only techniques. So even a single ARM core at this point becomes capable of running a machine learning model or deep learning model for something like wake word detection, which is quite substantial as a capability already for a number of device types, such as smart speakers. But we also see a very clear benefit for image classification, object detection, and other computer vision models that can run on ARM Cortex-A processor-based devices today, because the Neo service fundamentally reduces the overall footprint of that model by eliminating the need for a large, complex framework with a more compact runtime that fits within 2 megabytes of the device memory, as well as lowering the resource consumption of the model itself as it runs on that device. With that, I want to thank you for your attention. If you have additional questions, this is a good time to ask. Thank you.